This is the first example of two that we're going to look at on sort of shear flow and try to apply what we saw in the previous video where we did a real brief derivation for shear flow. So just as a reminder, just remember that shear flow is a determination of how much shear force occurs over a given length of the structure. And the structure which we have here is this built-up I section. It's made of three different boards, which are all 20 millimeters by 100 millimeters, and they're nailed together at a spacing of 25 millimeters, both top and on the bottom here. The project, or the question brief tells us that we have an applied shear force of 500 newtons. And what we need to do is find, well, what is the shear force in a particular nail? And the essence of this problem, and sort of to tie it back to general engineering terms, is that you might have worked out what all of your bending stresses are, your shear stresses for your boards, and they might be just fine. You know your design load is 500 newtons. You want to try a spacing for your nails of 25 millimeters, and you want to know that your nail can take a given capacity, and you want to find out, well, how much force is actually getting loaded into each of these nails. So that's really what the question's asking us. So if we ever see a question like this where we're looking at shear force for each nail, remember this is a shear flow question, and really what we're looking at is going to be the shear which is flowing along the flange, both top and bottom. Because we have a symmetrical section where we're going to expect our neutral axis to be right in the middle, and so our shear stress is going to be the same top and bottom. And if our shear stress is top and bottom with the same cross-sectional area, we're going to have the same shear force going in there. So for a shear flow question, it's always good when we set these up to look at, well, what's the governing equation? Shear flow, it's going to be little q equals VQ over I, and that's equivalent to V times A1 Y1 over I. So that's the one that we're going to be working with to try to find out what each of these forces are. The other things we need to find, just like with the shear stress profile questions, the VQ over IT ones, which we worked over in previous videos, we need to find our centroid of the section, so basically the location of the neutral axis. And we need to find our moment of inertia, our second moment area, this I. So we need those before we can do anything. So let's just work through finding those. All right, so Y bar. Remember that's just some of the little areas times their centroids over the sum of the areas, and that's going to equal 20 times 100 times 130. So that's just the area of the top flange. Just do FL for short, and 130 is 20 plus 100 plus half of 20. Y bar, we'll just call it TF for short, plus 100 times 20 times 70, so 100 times 20, this is just area of the web, and 70 is half of 50 plus 20. And that's Y bar of the web plus 20 times 100 times 10, and that's all just the bottom flange. And we'll divide that out by the sum of the areas. 20 times 100 times 130 plus 100 times 20 plus 20 times 100. And actually, that was my mistake. I didn't mean to put in that 130. So just, it's 3 boards that are the same area, so we should see that 3 times. We work all of that out. We get y bar equals 70 millimeters, which is what we would suspect for a symmetric section. It should be right halfway in the middle. Now, so we've got our y bar. Now we need to find I. And just remember, with I, it's we'll use the parallel axis theorem. So it's just the sum of the moment of inertia of each piece plus the area of each piece multiplied by the distance of that piece to the centroid squared. And if we work all of that, so the 2 pieces I'm going to use, or 3 pieces essentially, I'm going to find the moment of inertia of sort of the exterior of this box, and then I'm going to subtract out the 2 voids on either side of the web. I'm doing that because all of those pieces have their centroid at the same location, at 70 millimeters from the middle there. And so this d squared, so this d squared portion becomes 0. It's a lot simpler calculation. So we'll just work that out. So I equals 1 over 12 times the beam is 100 millimeters wide, and it's 140 millimeters tall, and so we'll cube that, plus, and the area is 100 times 140, and as I said, the distance to the neutral axis of this overall box is 0. And then I'm going to subtract out 2 of these voids here, and the contribution to the moment of inertia that those provide. So that's 2 times 1 over 12 times 40 millimeters wide times 100 millimeters tall cube. So I think you can see that. So the 100 millimeters tall. And then this is 100 minus 20 divided by 2 gives us our 40 for each of the voids, 2 voids, plus 40 times 100 times 0 squared, because the centroid of this void is in the same line at 70 millimeters where the centroid is of the entire specimen. So those go to 0. We work out these 2 components, and we get our moment of inertia equals 1.62 times 10 to the 7th millimeters to the 4th. All right, so now we have all of the constants that we need. We can work out what our shear flow is, and it's really a fairly straightforward calculation. It's only about 3 more steps and we're there. So let's just draw out our section again, just so that we've got the geometry down here while we're doing our calculations. So the centroid is right there at 70 millimeters up from the base. So that's 20, that's 50, 50, 20, and it's 100 millimeters wide. So if our shear flow equation is Q equals V Q over I. We have V, we have I. So V was given to us as 500 newtons. We just found I. We need to find Q. And we find the Q just the exact same way as we found it for when we're looking at shear stress profiles. Q is just A1 times Y1. And so this area 1 is the area above the section of interest. So our section of interest is right where these nails are going in. So we can even draw the nails just to... So, you know, it's our flange is going to want to move relative to this web. So this is our distance, or the location that we're interested in. This is A1 here. And Y1 is just the centroid of A1. And it's that distance to the neutral axis. So working out Q equals, so A1 is just 20 millimeters times 100 millimeters. That's A1. And Y1 is just going to be 50 millimeters plus 10 millimeters, since the centroid of A1 is right in the middle there. So we'll just call that 50 plus 10. So Q equals 1.2 times 10 to the 5th millimeters cubed. All right, so, well, we can figure out the shear flow now. And so remember, our shear flow is just going to give us our, shear flow equals shear per unit length. So shear flow, we go Q. If that equals VQ over I, that's going to equal 500 newtons times 1.2 times 10 to the 5th millimeters cubed over 1.62 times 10 to the 7th millimeters to the 4th. We work all of that out, we get Q equals 3.7 newtons per millimeter. So now that we know our shear flow, we know our shear per unit length, we can figure out, well, how much is acting on each nail. And the way we do that is we'll just draw a little picture. You think about it kind of as a tributary area. So if this is the top flange, and these are our nails, and they're spaced at 25 millimeters, well, kind of the shear, which is halfway in this tributary area, that shear is going to go into this nail. This shear is going to go into that one. And this one into that. So all we need to do to find out how much shear is going into a particular nail is multiply our shear flow by a distance. And that distance is 25. So it's halfway between the two, and because we've got both sides, that's 25. So the shear per nail, V nail, equals Q times 25 millimeters, and that equals 3.7 times 25, and we get V nail equals 92.5 newtons. So that's it. That's all that we have. So we'll maybe zoom out there for you so you can kind of see the whole thing. Yeah, so in order to find what shear is going into each of these for 500 kilonewtons coming in, it's really only a few little calculations here. So finding the centroid in I, we have to do that for most sections anyways. And then yeah, the Q, we've already had a lot of practice working with how you find Q, so that's just A1, Y1. And then it's a pretty straightforward equation. And then we just work out our spacing, and then that gives us our shear per nail. So we'll work with one more example on that, and then we will look at some more stuff with shear flow in terms of thin wall sections. But like I said, one more example to come.